Okay. So today will be the last lecture of this course. So let us start discussing the cross section of this particular process. So let us consider this process. Electron plus can you hear me? Am I audible?
Yes, sir.
Yes, Professor. Yes, Professor.
Good. So let us discuss this particular process today. And why I am discussing this particular process today? The reason is that this is an example of an inelastic scattering. So the process that I discussed in the previous lecture was the Compton scattering, which is the scattering of an electron and a photon. That scattering is an example of an elastic scattering. By elastic here, what I mean is that the initial particles and the final particles are same. And the nomenclature is that when the initial particles and the final particles are not same, this we shall call this type of a scattering process to be an inelastic scattering. Because the initial particles and the final particles are not same. And it is easy to see that to the lowest order, we want to calculate the cross section for this process at the lowest order, perturbation theory. So at the lowest order, there is only this diagram which contributes to the scattering. One. You just see the labels. The labels includes are P1 is on prime plus. So you can understand that this, when the arrow is this in this direction for the outgoing particle, so it means that the mu plus is the antiparticle of mu minus that is being created. The momentum in this direction is minus p2, so in that direction it is plus p2. Okay, so at the lowest order in perturbation theory, this is the only diagram, Feynman diagram, which contributes to the scattering cross section of this process. There are no other diagrams. And once again, as in the previous lecture, we shall work in the highly relativistic limit, that is both the electron and the muon, their masses, we shall neglect their rest masses because it is high, both the particles are highly relativistic. So that will simplify the calculation a lot. So since there is only this S channel, and you can see that this diagram is basically the S channel diagram, right? So only the S channel contributes here. And let us now apply the Feynman rules to write down the scattering amplitude for this process. So as I mentioned earlier, so let us start from this particle. So you can see that to be U bar S1 times P1. Then I have I, E, gamma nu. So I have gamma nu, and then we have, this is the mu plus. So this is basically the antiparticle of mu minus. Therefore, I have V S2 prime. So that completes this vertex, this and this. And now I have this photon propagator, right? I have this photon propagator. So
So that part is not visible.
which
The
part?
whole
I see. I see. Okay.
visible.
Okay. So I have to be careful. Today I have actually adjusted the Obhijit from the computer center has. I asked him to adjust the settings of this part. Otherwise, videos are not very good. This is not helping. So let me just come back. Okay. Can you see now?
Yes, sir.
IG new.
So what is after new, IG new? What is the last index?
Yes, I'm telling you. I'm writing down the photon propagator. So this part was this mu minus, mu plus, and the vertex. This part. Now you have the photon. The propagator, I have derived the photon propagator for you, is Ig nu mu by k square. I'm calling this momentum to be k. Okay? And then so this part you cannot see if it is Ig nu mu by k square.
Okay, sir.
Can you see? So from
Yes, sir.
here, I'm now writing here. So I've reached this point. So once again, you have to write down the factors here. The factors here are: this is the positron, this is the creation of the electron, this is the positron. Therefore, we have, so at this vertex, the positron is getting annihilated and the electron is getting annihilated. Therefore, we shall have P bar is S2 K2. Then we have I E, the vertex factor, comma mu, and then the electron is getting annihilated over here. So we have U S1. So that completes the amplitude, the scattering amplitude for this process. Is it okay? So now let us just simplify this a little bit further. So this you can write it down as, you have an I over here. So this I times I is gives you a minus. There is an I here, so I can write this down as okay. Here there will be a minus for the photon propagator. Minus I g nu mu by k square. Okay. So that gives us minus. So you can, what you can do is just take this minus out. Write it over here. So this is your expression for the scattering amplitude. You just need to calculate the probability for this process, probability of scattering. So you just take the mod square of this, and when you take the mod square, once again you have to sum over the spins of the final particles, and you have to average over the spins of the initial particles. So each of these are spin-off particles, electron and positron. So that will give. So there are 4 states. So you have to divide by a factor of 4. So what you need to calculate is 1 by 4 summation over s, summation over spins. You can just write it as summation over spins, all spins. So this factor of 4 comes because of this averaging over the spins of the initial particles, and then there is a summation over the spins of the final particles. So you have this, and then you take a mod square of this, so that will give us u bar S1 times P1. So that when you take, so you see that here you have an E, you have an E over here, so that gives you E square, and you are taking mod square of that, so you get an E to the power of 4. So E to the power of 4. And we will also get a factor of 1 by k to the power of 4. So you have 1 by k to the power of 4. And what is this k? This k is basically k1 plus k2. And also you remember the, so you cannot see this side of the board, just a minute. So now I am writing here, this k comes from this here, from the photon propagator. It is now k to the power of 4 because you have taken a mod square of that. But k from this Feynman diagram, you can see that this the momentum of this photon is basically k1 plus k2. So k is equal to k1 plus k2. And you remember the Mandelstam variable, right? Mandelstam variable by definition is k1 plus k2 whole square, right? So this is basically equal to, therefore this is k square, because k1 plus k2 is k. So s is k square. So since you have k to the power of 4, therefore this is s square. You just change it to s square. So you have s square in the denominator. Is it okay? You have s square in the denominator, and then you just write these factors. It will be gamma nu d is 2 prime d2. And what you can do is you can just contract this now. So this will become gamma mu. You can forget about this g nu mu now because you have used g nu mu to lower this index mu downstairs. So you have gamma mu. Then we have phi. I hope you can see this part. Then we have phi bar S2 A2 gamma mu. This times the complex conjugate of this thing, because you are taking a mod square. So the complex conjugate of that. So if you take the complex conjugate of that, what you will get is u bar S1 A1 to become gamma mu. So here gamma mu 3 S2 A2. Then you have B bar S2 prime E2. Then we have gamma mu u S1 prime. So this is the result of taking the complex conjugate. Is it visible?
Yes, sir.
So what I have done is this e to the power of 4 comes just from counting this multiply and then take square. 4 has come from the averaging process, sum over spins, and then there is a factor of 1 by s square, where s is the Mandelstam variable, and then you have this full thing, and just wrote it down over here, and then I took the complex conjugate of that, and this is this. So now you can see that there are 4 summations over, there are summations over 4 spin states, S1, S2, S1 prime and S2 prime. Okay. So let us now do the summation. So you can see easily that what you can do is you can do the summation over S1 and S2. Let us do the summation over S1 and S2. From this expression, you can see that, see, this is spin S1 prime, this is S2 prime. So when you sum over S1, S2, this will not contribute. Okay? This will not be there in the summation. So the only term which has S2 now is this, which starts from here. So let us write it down. V bar S2 K2 gamma mu 2 S1 K1. Then you have U bar S1 K1. Then you have gamma mu. Let me write here gamma mu. Then you have V S2 K2. And these terms do not have any S1 or S2. This is S2 prime and this is S1 prime. Okay. So this is, you can carry out this sum quite easily. So what I shall do, let us break it into components. It is better to break it into components. So let me write this as alpha over here. So you have alpha, then alpha beta. So this is alpha. Then this is alpha beta. This is beta. This is kappa. Kappa delta. This is delta. Do you follow this? The writing down of the indices. So what I have done is V bar it was S2, so I now put an index alpha, then gamma mu alpha beta, then U S1 beta, that completes it. Now U bar S1 kappa, gamma mu kappa delta, V S2 delta. Okay? So once we have written down the indices explicitly, what you can now do, now these are no more matrices, these are basically numbers, because these are the components of the matrices. So what you can do is, you can take this and put it over here. Okay? So if you put this factor over here, then it is basically V S2 delta K2, V bar S2 alpha K2. Right? So you can now perform the spin sum. The spin sum can be performed, and you will get from this factor and this factor. So I'm just cancelling these two factors. So what you will get is K2, and so this K2 involves the positron, right? This is the spin sum over the positron. So this we shall get this to be K2 plus the rest mass of the positron, and this was delta. This is delta alpha. Okay, is it clear?
Yes, sir.
You get this. Now, similarly, you can just look at this term. This also involves the electron and the positron. But this part involves the electron only. These are the electron spins, right? Coming from the annihilation of the electron and the creation of the electron. So for this also, if you carry out, so once for this you have carried out this mass spins, the sum over this spin S2. So this S2 is also gone. Now you carry out the sum over the spin S1, so this spin is also gone. And this one therefore will give us K1 plus or minus mass of the electrons. And now look at the component, this will be beta kappa. So now you have performed this thing sum, and therefore the result that we get after doing this is the following: gamma mu alpha beta k1, not k1 vector, this is k1 slash. This will also not be k2 vector, this will be k2 slash. Let's make this correction. This is not k2 vector, this is k2 slash. This is k1 slash. So this is k1 slash minus in beta kappa. Then we have gamma nu kappa delta. Then we have k2 slash plus mp delta alpha. And once again, in the highly relativistic approximation, you can throw away this mass, the rest masses of the electrons. You can forget about them, right? So these terms are not there, and therefore now you can see that this is gamma mu alpha beta, then this beta kappa, kappa delta, delta alpha. So this is nothing but the trace of gamma mu K1 slash gamma nu K2 slash. Is this clear? Is this okay?
Yes, sir.
You asked a similar question in the previous class where I did not break this up into indices, but today I just broke this expression into indices and showed you explicitly how the trace arises.
Okay, sir.
Good. Now inside the trace, you can always bring this factor here. You can just move the traces. You know traces are cyclic, right? The cyclic property for traces holds. For these are all finite dimensional matrices, so the cyclic property will hold, and bring this factor here, and you can play the derivative by using the cyclic property. So the sum over S1 and S2 is done. So now, therefore, this part is done. From here to here, this part is done. Let us do the sum over S1 prime and S2 prime. So now the remaining part that is there is S1 prime and S2 prime. Let us write down the expression for that. U bar S1 prime P1 gamma mu U S2 prime P2. Then the other part S2 and S1 it is already done. So what remains is V bar S2 prime P2 gamma mu to S1 prime. So we need to carry out this sum. So for that, let us once again break it up into indices. Let us call this alpha. This becomes alpha beta, and beta. This becomes say up lambda. This lambda delta. So we have now broken it up into indices. And once you break it up into indices, these are like numbers because these are the components of matrices. So what I can do, I can take this number and put it over here. And if you do that, then you can see that this is U S1 prime with some index, then U with some momentum P1, and then U bar S1 prime, the same spin, some index alpha, the same momentum P1. So you can sum over the spin S1 prime, and if you sum over the spin S1 prime, what you are going to get is the following. Now you should be careful because this is S1 prime, so it involves the outgoing particles. So that sum will lead to the rest mass of the muon, not the electron this time. Okay? So if you do that sum, then the resultant thing will be summation of the S2 prime, gamma mu, alpha beta, T. For this also you can do the sum, so let me just cancel the sum over S2 prime. So let us do this sum also. This will give us T2 slash B bar, so this will be mass m mu. So this is done, sum over S2 prime is done, and then we have this gamma nu factor, the gamma matrix, lambda delta, and this u bar will give us P1 slash u bar, so this will be minus m. But in any case, mu delta alpha. But in any case, we are neglecting the rest masses of the muon and the electron because it is highly relativistic. Therefore, these are gone. And now you can see that this is gamma mu alpha beta. This is P2 slash plus m mu. So this will be, you have to put in indices over here. So this is beta lambda, because this is beta and this is lambda. So there is an index beta lambda. So this gamma mu alpha beta, P2 slash plus m mu beta lambda, gamma mu lambda delta, P1 slash minus m mu delta alpha. So you can see that this is nothing but the trace of gamma mu P2 slash, because I've neglected a mu, this P2 slash gamma mu P1 slash. This you can write it in this way also. This is, you can bring this factor here using the cyclic property of traces. So P1 slash gamma mu P2 slash gamma mu. So that completes the computation of the sums over spins, the sum over the spins. Is it clear?
Yes, sir.
Good. So what we have done is let me come back to this part of the board. So it was required to calculate this sum over the spins for this expression. We have done that, and what we have found is that it is basically the product of two traces. So let me just remove this part. This part is the sum is now, we have carried out the sum. Therefore, the expression that we get is E4 e to the power of 4 by 4 s square, and then it is the product of two traces. The traces are of these matrices. So, this K2 slash gamma mu 1 slash gamma mu. So this is the trace of this one, which we got by summing over the spin S1 and S2, and then you have another trace, and that is the trace that I wrote down on the other side of the board, and I'm just writing the expression which we have already derived. P1 slash gamma mu P2 slash gamma mu. So ultimately, what we have computed, what we have obtained is the following: mod square of that scattering amplitude m square summed over the final spin states and averaged over the initial spin states is basically equal to this expression. So it now remains for us to calculate the traces of these gamma matrices. So now you have to just take recourse to the gamma matrix technology that you know. So you know how to calculate. There are, you can see, look at tables or appendices of books or any textbook where you can find the traces. And you should also work them out yourself just to check. And if you just apply these formulas, the formulas for the traces of the gamma matrices, then, so I hope you can calculate this, right? Because you can see that this is the trace of the product of 4 gamma matrices. This is also the same. So if you calculate these traces, you land up to will be 8 e to the power of 4 by s square k1 p1 whole square so this is what we shall do. So you use the same formula that I gave you to calculate the trace of a product of 4 gamma matrices. I have already given you a formula for that. And using that formula, I calculated the Mott scattering cross section. This same trace also arose in when you looked at the Mott scattering cross section. Mott scattering formula. The rather
Sir, sir, which one will be K2? I mean, you have
sorry.
uh, for the final result, which one will be K2?
I understand what you asked. Just a minute. Okay, here this is a good question that you have asked. You just need to use in proving this result. Once you calculate the traces, you need to use this kinematic identity, which is K1 dot P1 is equal to K2 dot P2. This is one kinematic identity, and K1 dot P2 1 dot K2 dot. So if you use this identity, you will end up with this expression. So first you use the formula for the trace of 4 gamma matrices, product of 4 gamma matrices, calculate the trace, and then use this kinematic identity. So I can show you one of the kinematic identities. So it's very simple to prove that K1 dot P1 is K2 dot P2. It is quite simple because from the overall momentum conservation, K1 plus K2 is equal to P1 plus P2, right? This implies that K1 minus P1 is equal to P2 minus K2. Now you take a square of both sides. So if you take a square of both sides, you will get K1 square P1 plus P1 square. Both are 0. P2 square plus K2 square, both are 0. We will get a minus 2 K1 dot P1 minus 2 P2 dot K2. So that gives you K1 dot P1 is equal to K2 dot P2. And similarly, you can prove the other identity. Is it okay? And this answers your question because here in the expression you will see that there is no K2, right?
Yes, sir.
There is no K2 in the expression. For the simple reason, because K2 we have actually eliminated it by using this kinematic identity in terms of K1 and P1 and P2. Use the kinematic identity K2, you can eliminate K2. Okay?
Okay, sir.
Okay. So now we shall calculate this expression. So this is the final expression that you have. Now we shall go to the center of mass frame. Let us go to the center of mass frame. So in the center of mass frame, if theta is the angle between the incoming electron and the outgoing mu1, that is between K1 and P1. K1 and P1. Then you can show that, let me first draw the particles in the center of mass frame. So you have this incoming electron. So this is your electron, this is K1, the 4 momentum, that is E1, E1 vector. Okay. K2, K2, okay. Is this clear? This is what we have. So this is the center of mass frame. This angle is theta. So this one is one plus b. So what I'm saying is, if theta is the angle of scattering between the incoming electron, this is the incoming electron in the center of mass frame, and the outgoing electron. So this is the angle of scattering. Theta in the center of mass frame, the core momentum K1 is K1 K vector, and the momentum of the initial particles should cancel in the center of mass frame. Therefore, K2 is K2 minus K vector, and similarly for the outgoing particles. You have this thing. Then you can show that K1 dot P1 is easy to calculate. It's not difficult. It's E. Okay. Can show this, and also P1 dot P2 is E plus mod E cos. So let us try to just see whether these expressions are correct or not. So let me go to the other side of the board, or maybe we can do it over here itself. You see that in the center of mass frame, the energy of all the particles are same. Each particle has the same energy E in the center of mass frame. That you can argue. It is a very simple. It is very simple to see that. And therefore, suppose you want to calculate Q1 dot P1. So what is Q1 dot P1? Q1 dot P1 is K1 mu P1 mu. This is K1 0 P1 0 component plus K1 I P1 I component. What is K1 0? The zeroth component of the 4 momentum K1, you can see that that is basically, so since all energy of all the particles are same, so you can just move these things. E. So all these are gone. So K10 is basically E. P10 is also E, so this gives you a E square minus. You can take this I upstairs, so this becomes P1 vector dot P1 vector. But what is K1 vector dot P1 vector? It is modulus of K1 vector, modulus of P1 vector times cos theta. So, you have this to be equal to E square. Since the rest masses are 0 for both the particles, therefore K1 vector modulus is basically the energy of the particle. So this gives you E square cos theta. So I can take E square common. So this becomes E square 1 minus cos theta. This is correct. Just so actually what I'm doing is in this expression, in the any going to 0 limit, you can replace this thing by E. So I can take E common, so this becomes E square. This is 1. So E square minus 1 minus cos theta, and similarly for this. So I've shown you the calculation of K1 dot P1, that is E square 1 minus cos theta. And in a similar way, if you proceed, you get K1 dot P2 to be equal to E square 1 plus cos theta. Okay?
Yes.
Ah.
Between K1 and P1, the angle is actually pi minus theta, so it will actually be minus of cos theta.
K1 and P1.
Yeah, that is
This is K1 and this is P1. So this angle is theta. Look at the arrows.
okay. I understood. Yeah.
Arrow, this arrow. So take the dot
Okay, sir.
product, theta.
Okay,
Okay.
okay, sir.
And let us see what S is. What is the Mandelstam variable? S is equal to K1 plus K2 whole square, right? But K1, so this is K1 square. K1 square is 0. K2 square is 0. So this is twice K1 dot, right? But what is K1 dot K2? You just see, if you just calculate K1 dot K2, you can calculate it just as we did the earlier case, and neglect the rest mass of the electron, then you will see that K1 dot K2 is twice of E square. So this is 4 E square. Is this clear, or should I calculate K1 what K1 dot K2 is? You see, K1 dot K2 you can very simply calculate. Just proceed in a similar way. It is basically E square minus this K vector square K dot K, right? This. It is K dot K. So this will give you K vector square. So this is a minus. But what is K vector square? It is approximately E square. To neglect the rest mass of the electron. So this is 2E square. So K1 dot K2 is 2E square. Therefore, S is 2 K1 dot K2. K1 dot K2 is 2E square, so S is 4E square. So the Mandelstam variable S, the S channel variable, this is 4E square. So you asked in the previous class what is the physical meaning of this Mandelstam variable S? It is basically related to the center of mass energy. You can see that
Okay, sir.
square root of S by, if you take a square root of both sides of this equation, you will get square root of S by 2 is equal to E. So the center of mass energy is basically proportional to the square root of S. So that is the physical meaning of that Mandelstam variable S. So let us proceed once again. So I have calculated K1 dot P1 and K1 dot P2 whole square of these quantities. So you just substitute it over here, and if you substitute those things over here, it is just a matter of very simple algebra. You will get e to the power of 4 into 1 plus cos squared theta. So how do we get this expression? We just substitute K1 dot P1 whole square here. What is K1 dot P1? It is e to the power of 4 into 1 minus cosine theta whole square. And K1 dot P2 whole square is basically, where did I write it? It is e to the power of 4, 1 plus cos theta whole square. 1 plus cos theta whole square. So just put it over here and simplify, you will get this. Okay? And now you can simply calculate the differential cross section with d sigma d omega. So what you do is, it is this quantity that we have calculated, and divided by a factor of, so let me just, it will be divided by a factor of 4 pi whole square, and from here you have e to the power of 4 into 1 plus cos square. Okay? And I think I missed a factor of s square. There is a s square sitting over here. Is it? Did I miss it? No, there is no s square. Just a minute. Let me just check the factor of s square. The s square here, this will be e to the power of 4. And then s square also you can put it in terms of p. So if I put this s square is basically 16 e to the power of 4. And we will put these expressions in terms of e to the power of 4, 1 plus cos theta whole square. And if you simplify, then the expression will be e to the power of 4, there will be no s square, e to the power of 4, 1 plus cos square theta. Okay? And now, the differential scattering cross section is this, therefore this will give us, okay, this is in the center of mass frame. You can show that it is basically e to the power of 4 by into 1 plus cos squared theta, 4 pi whole square by a division by a factor of 2x. This is the differential scattering cross section. I have not derived the formula for the differential scattering cross section in the center of mass frame, but you can look up into books where the differential scattering cross section expression for 2 scattering, means 2 incoming particles and 2 outgoing particles, is done. You can look into textbooks. It's very standard derivation. It's not that difficult. You can show that in the center of mass frame, d sigma d omega is basically the thing that we have calculated. So let me just introduce one more notation that will be easier for you. So far, what we have done is we have calculated this quantity, right? We have calculated this quantity. Okay? And the expression for this quantity is e to the power of 4, 1 plus cos squared theta. Let me call this quantity as m mod square bar. Let me introduce a new notation. The quantity that we have calculated is this, and let us call this quantity m bar mod square average. So if you use this, so the expression e to the power of 1 plus into 1 plus cos squared theta actually is equal to this object. Okay. If you introduce this notation, then you can show that the differential scattering cross section d sigma d omega in the center of mass frame is given by, you can derive a formula for that, is 64 pi square s. Which means that it is basically the 64 pi square, you can write it down as 4s and 4 pi whole square. So this 4 pi whole square gives you pi square, 4 square gives you 16, 16 into 4 is 64. So that is the formula that I wrote down, 64 pi square s times this. And therefore, this quantity is basically this. So I just write it over here, 1 by 4 pi whole square 4s. E4 by 4 pi whole square, you can write it down as alpha square. It's a fine structure constant because alpha I introduced before. It is alpha is basically e square by 4 pi. So this gives you alpha square by 4s 1 plus 4 square. Is this clear?
Sir, that 4s term is only for the central of mass frame.
See, this is the formula that you can derive for the differential scattering cross section in the center of mass. This quantity is basically this that we have calculated. That is the matrix element for this process that we have calculated using the Feynman rules for the diagram. And once you have this, you divide by a factor of 1 by 4 pi whole square 4s, which means 64 pi square s. So that is, it basically means that you divide this quantity over here by a factor of 64 pi square s. That is the differential scattering cross section in the center of mass frame. If you just do that, this will be the formula that you get for the differential scattering cross section for this inelastic scattering process. So, and you know that the differential scattering cross section is a measurable quantity that experimentalists measure in the laboratory. So this is a measurable quantity. Theta is the angle of scattering between the incoming electron and the outgoing electron. And the full thing is we are now looking in the center of mass frame. The center of mass frame, the energy of all the particles are same. This has a momentum k, therefore this has a momentum minus k. These are the incoming particles and these are the outgoing particles. This has a momentum p, therefore this must have a momentum minus p.
Sir, this entire calculation is done in the center of mass frame, right, sir? Yeah.
Up to this point, there is no center of mass frame. This was done in, we are not using any center of mass frame or whatsoever.
Okay.
This part, K1 dot P1. The center of mass frame we introduced only when we wanted to calculate what K1 dot P1 is, what K1 dot P2 is. Then we assume that we are in the center of mass frame, and then everything simplifies like this. The expressions for these, we just put those values in the center of mass frame.
Yes, sir, I understood that. I am just asking how are we getting that 4s term extra?
That is what I told you precisely. In the center of mass frame, you can show that the differential cross section, the formula for the differential cross section in terms of the matrix element and the Mandelstam variable is this.
Okay, okay, sir. Yeah, it is clear. Okay, sir.
Okay, that
Okay,
you can
sir.
you just look into any textbook, any quantum field theory textbook. You can show that for 2-2 scattering, two particles scattering initial two, we have two initial particles scattering to two outgoing particles. This is the general form. Where this part is this averaging over the matrix element mod square, which we have calculated. This thing in the center of mass, this thing basically becomes E4 1 plus cos square divided by this 4 pi square, 4 pi whole square by 4s. Is it okay?
Okay.
So this is an example of an inelastic scattering Now there are other scattering processes also. For example, you have the famous electron-electron scattering. So two electrons scattering to two electrons. This is once again an example of an elastic scattering because the initial particles and the final particles are the same. Then you have the Haba scattering, which is basically the scattering of electron-positron to electron-positron. And there is a very beautiful symmetry here, which is called which is known as the crossing symmetry. So it basically says that you have electron-electron going to electron-electron. Now you just take the electron on the left-hand side on the other side, and take the electron on the right-hand side to the left-hand side. It gives you the Haba scattering, which is basically the electron-positron scattering. So there is a this crossing that you have done. It is called a crossing symmetry. And why is this crossing symmetry very beautiful or very important in some sense? It is for the simple reason that if you can write down the amplitude for one process, for example, the electron-electron scattering, you can immediately write down the amplitude by using this crossing symmetry for the electron-positron scattering, because there is a nice symmetry between the two. We have discussed the quantum scattering, we have discussed the Rutherford scattering, the relativistic scattering, correction to the Rutherford scattering, this is the Mott correction, Mott formula. We have discussed the quantum scattering, and now we have discussed today the electron-electron going to mu minus and mu plus in elastic scattering. I would ask you to try and calculate or at least write down the amplitudes for the electron-electron scattering, which is known as the molar scattering, and the Haba scattering, electron-positron scattering. Just if you can write down, if you can identify what are the possible diagrams there, and then just calculate at the tree level, because we are doing tree level calculations. Just identify the Feynman diagrams and write down their amplitudes, and then try to take mod square of those amplitudes and see what you do. So thank you very much. Today's lecture will be the last lecture of this course, because for the next 2 weeks I shall not be there, and it will be very difficult for me to take the classes online because I will be busy for some personal reasons. So let us end the course here. You may just send mails if you have any doubts regarding the course that we have gone through over the last 4 months. You just send me some mails. So if you have some doubts, I will try to answer. Okay then.
Can you please suggest any book for this cross-section calculations? I could not find it properly.
You can look at Peskin's Rider, quantum field theory. You can look at this book, Quantum Field Theory by Ryder. You can also look up into Quantum Field Theory by Amitabh Lahiri. So you can look. There are many books actually in quantum field theory. So you can look Peskin's Rider, Amitabh Lahiri, Physics and Zuber. Any book, whichever book you feel comfortable. Just take a book. There are lots of good books in our library. So you just take any book and try to see it. Okay?
Yeah. Okay, sir. And sir, I want to say something.
Yes, please.
Thank you for teaching this course in such great detail and explaining all the things in proper way. I think you have done a very good job while you have explained everything in very detailed way. Thank you, sir.
Thank you very much. So it is a pleasure that you have liked these courses. So these lectures. So it would be very nice if I could have taken some more lectures, but I will not be there for the next 2 weeks. So let us end it over here, and just go take any. If you can see nowadays, you will get all these books in the. You can get soft copies of them also. So just download those soft copies and you can look into those books. Okay.
Okay, sir.
Thank you, sir.
Thank you.
Thank you, Professor.
Thank you.